Afternoon, everyone. Apologies, you get a very slightly shorter lunch break than others, but I'm sure it'll be worth it. So welcome to Energetics, the Future is Explosive. I would like to welcome the speakers. That would be Justin, who's a Dstl fellow, and Alison, who is a senior scientist. So over to you, Justin.
Good afternoon. Can I have the next slide, please? My opening slide. Well, I hope you're all sitting comfortable. You probably feel as hot as that bomb disposal officer in that image there. So without further ado, you pretty much know what this subject is all about. So on to the next slide, please. So what I'm going to cover today really is the aspects of what Dstl does in energetics, what our requirement is, how we collaborate with others. I'll give you some examples of the kinds of technology that we're interested in, and then I'll hand over to my colleague who will propose a specific challenge that we want assistance from the community with. Next slide, please. So by way of introduction, I'm Justin. I'm a Dstl fellow in energetics, energetic materials. My colleague who will come on later on in this presentation is Alison. You'll see, and I'll start off with, hopefully you'll see a video there of our Dstl logo illuminated using detonating cord. Which pretty much sets the scene where we're going about here. There's a case for understanding energetics, the diagnostics, new energetic materials, but you know, there's an element of intrigue, some decent science, investigations, and there is an example here. It looks a bit of fun making Dstl logo in explosives, but actually that session there was to train our staff, their competence, and actually about multi-point initiation on how you initiate the letters all at the same time, as well as the camera work. Next slide, please. So first of all, I'd like to define what I mean by energetics, energetic materials. These are essentially propellants, explosives, and pyrotechnics. We find that energetics are a critical and underpinning technology across a lot of defense and security for obvious reasons. So there's some examples there, images of some examples of where you will find energetics. Some of them are fairly obvious, some are maybe not so obvious, but they're running from left to right. On the left hand side you have a warhead producing an explosive effect against a land target. As you move to the right, you've got a 105mm shell, which could be filled almost entirely with maybe an RDX TNT explosive composition, or a smoke or an illuminating composition. Moving on to the next image, where you've got looks like a rocket. That is actually our strategic deterrent for the UK. That is Trident. So there are energetics in that system. Moving again to the right again, you have the MBDA's Sea Scepter missile, Sea Viper missile, and that's there. So launched from HMS Defender. But you can see there the energetics component there is the propellant driving it, and you've also got an energetic component in the warhead as well, about 15 kilos, I believe. Moving down from that image, you have an air platform where you have energetics in the form of pyrotechnics in sort of aiding the platform survivability. So you've got some flares being released from that aircraft to protect it from any incoming threats. So there's pretty much energetics are subcomponents of larger systems, and they are very important ones as well. So in simple terms, energetic materials are a very convenient store, a high density store of energy, and that's why they've been used for many systems for many years. However, UK's the mission requirements, what we require from all of our materials is rapidly changing. The kind of missions that we want to do, the kind of environments where we want to operate in, does pose challenges. You know, these are metastable materials, and we want to put them into more extreme environments, and actually we want a bigger effect, a more reliable effect, and safety is quite key. So I'm now starting to introduce where our requirements are coming from. Next slide, please. Thank you, Brian. So pretty much our DSTLs has some fundamental underpinning science and technology requirements in energetics. And ultimately, this is to ensure that within the UK, we've got access to this S&T that it needs now for operational reasons and for the future. And it mostly is to do with supporting our national capability. So DSTL's remit is really the stewardship of capability. We're very interested in the exciting blue skies research. We are a threat-based organisation. We do provide evaluation of what could be used against our national interests. And often many of them contain explosive components, but we also provide a wider advice capability to MOD and other government departments. Next slide, please, Brian. So I could spend, if anybody knows me, I could spend many chapter and verse talking about energetics. In a nutshell, these are the key requirements that Dstl. This is what we do in energetics in a daily basis. As well as advising on new weapon systems to come into service, because we have to look at the whole life of those systems. Safety is a key component. Energetic materials, explosives, they are potentially hazardous if something goes wrong or not used or used incorrectly. We're very interested in, disposal, novel materials. There'll be more said about that in a minute. New ways of manufacture. Obviously, the whole materials science industry has come on leaps and bounds since the Second World War, for example. There's massive advances, and energetic materials, they are materials that in themselves, they do need, we need to evaluate their structural response, their strength, etc. Obviously, if we're interested in these materials, we need to have a diagnostics capability to understand them, to characterize them, to evaluate their performance, as well as their effectiveness. And this certainly does come across in when we're looking at threats from explosive materials, such as terrorist threats, bomb disposal. You'll see an image there where there's a robotics means of neutralizing an explosive threat in a van. So when you hear on the news a controlled explosion was carried out on an improvised explosive device, that was a weapon system concept and disruption concept that was developed within Dstl and its former agencies. We're also interested in, energetic materials are commodities. They are, we got security of supply of these chemicals that go to make energetic materials, and a broad piece of what we do, a lot of support to national security and military operations, both homeland and abroad. But what a key thing that people probably don't understand is actually and Dstl in the past has provided a pipeline of suitably qualified and experienced persons. You may hear the term SQEP said quite a few times, but we, in order to understand energetic materials, to characterize them, it's very difficult to gain those skills in an appropriate manner. It requires unique facilities, and not everyone has access to them. So there is an element there of that Dstl does in providing stewardship of the capability, and that's one of the reasons why we do get asked for a lot of fundamental advice. Next slide, please. So we don't, Dstl always delivers our work in a collaborative manner, and within the energetics area, we deliver this through a construct called the COEM, the Centre of Excellence in Energetic Materials. This is essentially all government departments. It's a government-led construct. All the government departments in the centre there that you can see in that figure, who have an interest or a stake in energetic materials, are involved in this construct. This helps in coordinating all the research, training of staff, knowledge management, guidance and advice. So anything that is proposed to us will get visibility across this wide audience. And that's one way in which we avoid duplication, avoid working in stovepipes, and work with the wider community to ensure that we can all benefit. You can engage through this through their various contractual mechanisms with individual organisations. We try our best to coordinate these things through those contractual frameworks, which more will be said about that later on in the next session. Also through some industry groups as well, such as the Institute of Explosive Engineers. I won't dwell on it anymore. If you want any further information, there's a web link there, www.coim.org. Next slide, please. Next slide, please. No, thank you, Brian. It's there. Thank you. Just to give you an example of the kinds of technologies, exciting technologies that we get involved in energetics, I could not have a presentation without showing some of the absolutely superb science and really exciting research that goes on here. If I start on the left-hand side, at the bottom, you see an image there of a 3D printing head. And there's some work there where we're looking at can we apply additive manufacturing processes? Can we print explosives, energetic materials? Can we make all kinds of varying charge shapes? The possibility there is endless, and it opens up a whole new world of novel of charge design for us to explore. And that is something that we're embarking upon now. It's of great interest. But also, you know, key things there is that we need materials there that can actually are actually printable with that equipment. Just above that, there's an example. It should be a video playing of a mixer above the printer one. Brian, I don't know whether you can get the video to play next to that under novel manufacture. It doesn't seem to be playing. That is, if it is, I'll just move on. It should be showing a bladeless mixing process where it essentially it's like called resonant acoustic mixing. Essentially, mixes materials without having anything incorporating into the material. It's a very novel, a very efficient method of manufacturing, making energetic. There it goes. The video is going now. A very efficient way of manufacturing materials. Gives some very good mixing. So there we would use like mixing explosive crystals with binders would be an example there. It's very similar to the paint mixers that you might get in your local B&Q. Your attention's probably been drawn to the video playing at the long video playing at the top of the screen, which shows an explosive charge, a shock wave transiting across the screen, and then fragmentation coming out and hitting a plate. That's an example of reactive materials. We're interested in reactive fragments, so fragments that actually, when they impinge on a target, they produce an energetic effect, which is novel, novel threats as well as can be novel technology. We're also very interested in new materials. We want new molecules. We're interested in making safer formulations. We want greater performance, so things that detonate faster with more pressure. But we're also interested in nanoscale materials as well, because there's some unique properties that could be obtained, such as safety properties or performance properties that can be attained by reducing sort of crystal scale. Right over onto the right-hand side of the slide, you know, I've mentioned diagnostics. You know, we're always looking at new tests, qualification tests. How can we put these materials into service with our military users safely? Requires a lot of diagnostics, ultra fast diagnostics. These are fast events, and also provides a knowledge base for when there are problems that we've got people, this right skilled people to be able to solve them. So I've just given you a flavour of what we get up to. Next slide, please, Brian. Next slide. I think there's a bit of a lag in the slides here. I'll just wait a second. You can see some images there of some bricks which look, which have a like a line through them. There's an example there of how you can improve shape charge performance through lumps of metal, basically. This slide here wants to give a vision. If I was going to send a postcard from the future, as to what would energetics materials be in the UK. Here is just an example, one of the many examples I could give, but here's an example of how we would apply that to manufacturing. To explore, the generation after next technologies with developing people in between. So from the sort of war era, it's bucket manufacture, which is like fixed, it's costly. This is like big bucket chemistry of big mixers, filling bomb shells, cases, very much old technology. What I see in the future, and this is a technology vision shared by the COEM, the Centre of Excellence in Energetic Materials, is moving to more precision energetics, flexible, agile manufacturing. There you've got a flow chemistry rig set up of using manufacturing the energetic molecules. You have a 3D printer where you could print the outside charge construct, and then you have, on the bottom right hand image there, you have a large platform resonant acoustic mixer where you can mix the energetic material actually in the warhead. So you're going from a very much a commodity to a chemical or energetic material to a more specialist niche area. I've given you a flavour of what we do in energetics as our requirements. I'm now going to hand over to my colleague Alison, who will give you a challenge of what we've got specific interest and some outreach that we want from the community. So next slide, please, and I'll hand over to Alison now. Thank you. Alison, are you there? You're on mute.
Good afternoon. I hope you can hear me now. Sorry about that. So I'm going to introduce the Advanced Energetic Materials project that's recently been funded as a result of the strategic review. And it's a project that we're currently in the process of setting up. It's very early days. We're working at pace, and it's a really exciting challenge for us all. So the aim of the project is to accelerate the discovery and delivery of new energetics materials and explosives for future use by UK defence and security. Next slide, please. So before jumping into the technical content, I'm just going to summarise the main drivers behind the project, some of which Justin has touched on. The bottom line is that we need new energetic materials. These are a fundamental and underpinning technology across defence and security, and we need to maintain the military advantage. We know our adversaries are working on new technologies, and we need to keep pace. We've also got a wealth of new technologies that have become available and now can be applied to the energetics area. For example, flow chemistry and resonant acoustic mixing, as well as the automated processes, artificial intelligence, machine learning. And we're hoping that a combination of these new technologies could really bring us a step change for energetics. There are lots of potential advantages to new energetic materials. One of the key things that we're obviously very sort of interested in is performance and the energy output, but that there are also other aspects to consider: environmental impact, cost, and security of supply is another main theme. Okay, next slide, please. So the Advanced Energetic Materials project is funded out of the strategic review from 2020, and the aim is to accelerate the discovery and delivery of new energetics for future exploitation by UK defence and other government departments. And the focus of the project is going to be very much on using automated processes to both accelerate the discovery of new materials, but also to identify alternative synthesis routes for these materials, for the new materials, and for some of the existing materials that we know about, but we don't have a good synthesis route to. So as well as the actual future capabilities that the project will hopefully open up, this is also a project that will support the wider strategy for UK energetic SQEP development. It's a 4-year project, just started, as I said, and there's £9 million in external contracts to be placed. A very rough breakdown of that is starting fairly smallly this year with 1 million, going up to 2 million, and then 3 million in years 3 and 4. Next slide, please. Next slide, please. So we've got another lag, I think. So this slide sort of summarises some of the key words and the requirements transposed from the project mandate. So the challenge is all around looking for major step changes in performance rather than just small incremental improvements. We're really looking for novel approaches to get whole new energetic materials. We will work very much in collaboration with the COIM, which Justin talked about, and as much of this project needs to be placed, the work will be done externally. So we're keen to work with academia and industrial partners to really push for innovation and invention. And if at the end of 4 years that we have managed to identify new materials that can be produced and are safe to be used, then we will have succeeded. Next slide, please. So the next couple of slides are about the kind of technical themes within the project as it stands now. This is very much our starting point. This is a low TRL project. The research could really go in many different directions, which is what makes it very exciting. But this is the way that we've kind of approached it at the moment. So we've got 4 main work packages or technical areas. So I'll just run through each of those now. So work package 1 is all about discovery. Using machine learning and artificial intelligence algorithms to search for new energetic molecules in databases of molecules and materials that we've never previously explored. So these types of automated processes open up just, magnitudes of order in terms of numbers of molecules and materials that we can look at that you just can't do by other methods. Work package 2 is all around machine synthesis, the use of robotics, but also machine learning and AI again, those automated techniques to undertake high throughput screening or retrosynthesis to look for synthesis routes to these new materials. So it might be the materials coming out of work package 1, but also it could again be current known about materials and molecules that we don't actually have synthesis routes that are easy at the moment. So looking for alternative routes. Next slide, please. Work package 3 and 4. So 3 is the use of alternative chemical synthesis approaches. Again, looking for new routes to existing materials and new materials, and also considering looking at the energetic precursors and routes to those. And 4 is very similar, but this is using synthetic biology to look for those alternative synthesis processes. Next slide, please. So in a nutshell, we need new energetic materials. We're really early in the project. At the moment, we're kind of in that internal and external engagement process and drawing together, writing our statements of requirement. We're really keen to engage with you. So if you have any ideas, if anything has sparked during this presentation and you think that you could be involved in this project, then please use the email there on the right hand side. We've set up a project email and all engagement is welcomed. So as I said, we're writing our standard statement of requirements at the moment. Those will be going out in a matter of weeks using the various Dstl commercial frameworks. I'll sort of signpost you to the following presentation by the commercial department, which will tell you how you can engage with us. Also, I need to tell you that we have a Searchlight event planned in November. Thank you.
Thank you, Justin and Alison, and your enthusiasm is really obvious from what you've said. And what it has done, however, is squeeze our time a little for Q&A. But that's lucky because the audience has been so enthralled. We've actually only got one question. There is time to squeeze another one in if anyone wants to quickly type one. So within novel materials, how much of the priority is the reduction of SDT/XDT through armouring or new structural materials on the munitions themselves or their packaging. I'm sure that means something to you.
Thank you, Selena. I'll probably best at answering that one. So for those of you out there in the audience, SDT means shock to detonation transition, and XDT means unknown to detonation transition. These are a priority very much for our partners in defence equipment and support, who are very interested in the safety of these of munitions in weapon systems. It's of high priority for them in terms of the through service life of materials. And you can design at the system level what they call insensitive munitions, and you can change the packaging. You can design your packaging or the whole of your weapon system to be more, we call it insensitive, less likely to be to go off from an unintentional stimulus. So it's a priority for the whole of defence. It needs to operate safely. We don't want to have own goals here. However, for this particular project that Alison has mentioned, our priority, we're going to start with we want performance in our materials, and then we will look at those mitigation options in making them less sensitive, less hazardous, further down the line through extensive collaboration with our colleagues in DE&S. I hope that answers that question. Over. Are there any more questions?
Yes, I don't see any. Let me just look on the chat. No, I don't see anything there. Thank you very much, Justin and Alison. And we'll probably close this session now because the next one starts at 13:50. So you can either go across to the autonomy bit of machine learning, machine speed, or you can come along to the one at 13:50, which is transforming cyber resilience. And if you want to know more about the Searchlight, we're going to put that on social media, and there's a gov.uk information pack that we will also put out, so you can put that specific date in your diaries when it's set. So thank you for listening.